artificially, okay, to increase the dimension of the torus and the number of action angle coordinates, and that's why we're getting an actual polytope with half of the dimension of the manifolds, because indeed what we were doing, coming back to your beautiful picture at the beginning, is to take the polytope or the Delson polytope that corresponds to one of that symplectic leaves on Z and increase it with this modular vector field. So the modular vector field is very important in bisymplectic geometry. Exactly.
Indeed.
Exactly.
Indeed.
That's fantastic. Sorry, I was stepping over your argument.
No, you're embellishing the surprise in this case, exactly. Because indeed,
will I get $1 million?
Oh, do I?
I'm ready.
Okay, so here I wanted to write out very distinctively these two directions. So this Z is indeed the function that defines the hypersurface locally. So here we're applying, let's say, Darboux theorem or B-Darboux theorem in our case. This T is precisely the direction of the modular vector field. So this direction is the one that is transverse to the leaves of the symplectic foliation inside of Z. And for the other coordinates, I preserved X and Y. But in this case, I wanted to have T as a very specific function, let's say, a very specific coordinate in this case. Mm-hmm. Mm-hmm. So it's important to remark, I think, that the modular vector field, of course, is a B vector field. It is still tangent to Z. And also, as I say here, it's transverse to the leaves of the symplectic foliation. And if I may add, you can think of it as, this is not Hamiltonian, but you can think that it is B Hamiltonian because it's the function, the vector field corresponding to the function logarithm of Z.
Perfect. And their logarithm of Z is not a continuous function anymore. It's continuous with the right glasses, right? It's continuous with the pink glasses, not with the glasses that are not pink. If you put your pink glasses, the logarithm is smooth at 0 because you change, indeed, you change the bundle. Mm-hmm. Fantastic. That's very good.
Yeah. Are there any questions? I can go over any of the computations if anyone wishes.
Please go ask questions now. The people who have questions about these computations. Indeed, I asked Joaquim to do these computations because I realized that computations, like in the class of problems, were a strong part that people were appreciating, to have explicit computations in coordinates. As you can see, things can be really computed. So if students have questions, can you ask them now? Do you have questions?
Teacher, I have a question.
Mm-hmm.
Yeah.
What are the properties of a vector field on a self-track manifold?
Can you repeat the question? We didn't hear very well.
What are the properties of a vector field on a self-track manifold?
So the B vector fields, they have to be tangent to the, so a B vector field is a vector field which has, I mean, it's any vector field. No, it's not any vector field. It has to be tangent to this critical set. And the critical set in the coordinates of Joaquim is given by Z equal to 0. That's what you're asking, right?
Right.
Mm-hmm. Yeah, so in this set of coordinates, you can think that the basis of the vector fields, at least locally, are partial with respect to T, all the partials with respect to X or Y, all the X's or Y's, and also Z times partial with respect to Z.
Okay, thank you.
You're welcome. More questions for Joaquim?
Excuse me.
Yeah.
We are hearing you very low.
You are very low. Can you speak louder?
Okay.
Can you maybe be close to the microphone?
hear me?
Very low.
Very,
We hear you very low.
sorry. Can you hear me?
Ah, now yes, yes, we can hear you. Thank you.
I would like to ask what the symbol after EXI means.
This wedge symbol is the exterior product between one forms. So it's the product of forms.
So you have an anti-symmetric form. Think of a vector space. Okay.
Okay.
You take anti-symmetric vectors. So because you have an area form, when the property with respect to the tensor product, let's say, the difference is that when you change the order, you change the sign with this wedge.
Okay.
That's a very short way to say it, but I don't know, Joachim, you want to add something?
Okay.
Is that clear?
Okay.
Well, that's good that you ask these questions. I mean, I think this is very helpful for us because we had a planning of the course, and I think it's good to adapt yourself to this. So, I mean, I know that there are people in the audience from different backgrounds, but ask questions. I think this is very important. More questions. Okay. If there are no more questions, maybe Joachim, can you show these results on abstraction theory and then I take over, or what do you want to do?
As you wish.
Or you want to go back to the picture? I mean, we are going back to the picture indeed at this moment. This is, let's say, the formula that describes the picture that you were showing us at the beginning, right?
Yes. Yes. Second, I will stop sharing. I will send you these slides, Eva, so that they are added to the web page.
Thanks for this. I think this is very convenient because, I mean, it's good to have people trying to do, you'll have all the list of problems with the solution, but try to do them now that the course is over, even without the solution. And this gives you a test if you are doing this computation right or not. Okay.
So in this picture, we had this coordinate Z in here that we will, and we had this direction that is transverse to these green leaves which are the symplectic leaves on our exceptional hypersurface, and this direction that is transverse, this arrow in here. Wait a second, it's not drawing.
No.
1 second. It takes one.
We need to buy you a new iPad, Joachim.
No, it's fine. No, it's the pen.
Research group.
Okay.
Too old.
And this direction in here is the T that we had 1 second ago. So to rehash, here we have. Wait up. To rehash, here our omega is dz divided by z paired with dt, and here we just have the x's and y's, let's say. So the modular vector field in this case of the area with respect to our b-symplectic form, it is this one, perhaps with a Hamiltonian vector field.
Yeah.
But the interesting
you have
thing
this
is that
freedom of the Hamiltonian vector field. Remember that this is measured by this computation that Joachim did. This depends on the metric. This depends on the, this depends on the volume form. If you change the volume form, you have this Hamiltonian term, which is given by the coefficient comparing two volume forms, okay, by the quotient. But at the end of the day, I mean, there is a way to give to associate a cohomology to this, because and the cohomological point of view that it's in the notes. I mean, it's in the notes and it's in the problem session, but maybe it's a bit too hard to explain now. It's a cohomology. It's Poisson cohomology. but it's in the list. And it's very well written by Joachim. Huh? It's very well explained.
Yeah, in problem number 2, you can find this.
You can find this. So in terms of, let's say, in terms of Poisson cohomology, what you do when you can take the Poisson class of a vector field, and essentially two vector fields are equivalent. In the first, I mean, a Poisson vector field gives you a cocycle in that cohomology, okay, because the cocycle condition is the condition that it's Poisson. And then the condition that you have this Hamiltonian, two vector field, if they differ by a Hamiltonian, they represent the same class. Yeah, we cannot, I mean, Joachim and I have something in common, which is that we like a lot cohomology, right? So
yeah.
if you can say it with a cohomology, it's better. And that's like, that's what Pablo would call, this is categorical. For us, cohomology is important. If we can say this with cohomological words, precisely, this is the quotient of Poisson vector fields with Hamiltonian vector fields. And then in the quotient, that we didn't have time to talk about Poisson cohomology. This is just a mini course, but it gives you a little bit the spice of that there is something there. There's some classification controlled by some cohomology again. And that's a little bit the spirit in b-symplectic geometry. Like in the two-dimensional case in symplectic geometry, the only cohomology was Moser, and the Moser path method tells you that the important thing is the RAM cohomology. And here, the replacement of the RAM cohomology in a way is Poisson cohomology. And the good news is that for B Poisson manifolds, these guys, you can compute them as the B cohomology. And Joachim knows this by heart because he used this at least once every day, which is the Matteo-Melrose formula, right? That relates the B cohomology. Maybe you can write it there. Like, well, there is a theorem that I will also show in my slides that we already mentioned on the second or third day of the course that tells you that the B cohomology, it's isomorphic to the Poisson cohomology. And that was a relief, huh? Because Poisson cohomology is very hard to compute in general. And B cohomology is very easy to compute. And then if you know that they are isomorphic, then it's better to compute B cohomology. Okay. Why it's easy? Because as Joachim is writing, this cohomology, you can read it from the RAM cohomology just by considering the same degree the RAM cohomology. And then, of course, the critical set contributes also in the B cohomology. How it contributes? It contributes in degree -1. There is a -1. I see a plus, but it's a minus.
Sorry, no, but that's in homology. In cohomology, doesn't it go up one degree?
No, in cohomology, it decreases in one. In cohomology. I mean, we are writing cohomology right now.
Yes.
Yeah.
Yes.
Yeah. I know that you are thinking exactly. That's the situation. Then in cohomology, I mean, remember that when we were applying this to surfaces, then in cohomology, it gives you the H1, Joachim, exactly as it has to do. Otherwise, it will give you the H2.
Yeah.
And this is
That's right.
The
So I was thinking on homology.
Yeah, I remember this proof that we were trying to do a couple of years ago. Okay, this is exactly Matteo-Melrose formula, and that's a winner formula because it allows you to compute this cohomology, this Poisson cohomology, just using the standard rank cohomology. If you don't like the rank cohomology, take any cohomology, singular cohomology. They are all the same. I mean, this is what the RAM theorem is telling us, right? I mean, even Floer, this is something that I wanted to explain the last day of the course, no? But finally, maybe I will not. But even Floer came up with a new definition, said, I have a new cohomology. And at the end of the day, it was the RAM cohomology. So, okay, that's fantastic. That's very good. And well, maybe you want to comment a little bit. What do you want to do, Joachim? Do you want to comment a little bit the problems where we can see the proof of this other abstraction theory for b-symplectic? Yeah, sure. Because today, I mean, when I explain, I'll talk about this B contact theory, okay? And then you'll see how interesting these are related. Okay.
Yeah,
you wanna show?
I'm looking for the solutions.
Well, you can also project, if it's easier for you, they are online.
Yeah,
and I
through.
posted them yesterday night, so the server should behave. I didn't check if.
Yeah, but we are looking. But you're meaning the exercises on the first list, right? The exercises on the abstractions.
Yeah, but solutions are also on the they are all of them. Yeah, solutions are on the website.
Sorry.
Yeah. Yes.
Excuse me. Sorry, my network is not very good today. I have a question. Why h1 pi is equal to this ratio?
Yeah. So hello, Jayang. Now you put your name, so I hope that by the end of the course I can pronounce it properly. Jayang Li, welcome.
Field or Hamiltonian vector field.
Yeah. So how do you know? Your question is, how do you know that the Poisson cohomology?
Yes.
I mean, this first thing.
Why?
Well,
we have not.
We have not given the definition in this course of Poisson cohomology. But if we had, I mean, well, I said it very quickly. If we had, I would have said, just to answer your question, that the differential in this complex in Poisson cohomology is given by the bracket with the Poisson structure.
Yeah,
therefore,
actually, I can show the problem
that's
on
fantastic.
this 1 second, where we will have the definition.
Good. Then it will be more clear. Thank you very much, okay.
Thank you.
Yeah. So here is the complex.
Yeah.
It's here is the differential. So it's a little bit cumbersome, but we had this bracket, this Schouten-Nijenhuis bracket that relates alternate products of vector fields, so multi-vector fields. And the trick is, given one particular Poisson structure, which is a degree 2, so a bivector field, this differential you can define from one of these algebras to the next one by just pairing by the Schouten bracket whatever multi-vector field that you have. So if you actually you can work out this exercise if you want, or maybe we can talk about this here. We can solve this exercise, but basically in the particular case of degree 1, the cohomology given by this complex cochain represents what we said. So we spelled out actually the solution of this exercise, but we didn't explain how to do it. So there's still the intrigue. But basically, you can see that the kernel of the degree 1 differential is the set of Poisson vector fields. So they are the vector fields that preserve the Poisson structure, and the image of the one that goes before, so the degree 0 differential, its image are the Hamiltonian vector fields. So that's what this represents in this case.
And that's a computation that we did, because if you do the bracket of the function with pi, this is the same as computing the Hamiltonian vector field.
Yeah.
Let's say that's a difficult exercise, but let's say it can be done with the information they have. Yeah.
Yes. Yeah. So this is a good exercise in a way to go back to rehash the whole course, let's say.
Exactly. Perfect. That's a good way to say it. Was that clear, Jayang? Yeah, she had some problems with the internet, so maybe she's not. I mean, she will. Are you there? Maybe. Okay. She told that she has some problem with the internet. Okay.
My network is not very good.
Okay, I'm sorry. We were asking if this was clear. This was helpful, at least. Maybe you can, maybe Yang, because your network is not working, you can look at the video when we post it today and then ask questions, or we meet some other day? Yeah, I mean, well, I think she has some problems with the network. So I think we can go on. That was very clear.
Okay, thank you. Thank you.
Thank you,
Thank you.
Jiayang. Okay, so talking about abstractions, okay, in that list, well, perfect, that's very nice. There are several problems. Do you want to comment something especially about that? The sphere, no? We don't like
Yeah, here we have the high dimension sphere, let's say in this case S4. So I'm sorry, I don't want to jump again to the iPad, but recall that we had this foliation inside of the singular hypersurface by symplectic structures. So we can think that that foliation can, in some cases, define a symplectic structure, let's say globally. So, but in 2 degrees less than usually, let's say. So this is what this theorem is giving us, the Marcoux-Osorno theorem.
So it's capturing, let's say, the restrictions to have a symplectic form on this codimension one. That's exactly what this captures. So because here an important result is that if you have a compact manifold, then a symplectic form is given you in H2, a non-vanishing structure. And then from that, and from this very beautiful picture that you did, we can conclude such a result with a little bit of work.
It's important, perhaps it's good to recall that usually in the symplectic case, we have an explanation of why S4 does not have a symplectic structure, which coincides in this case with this one. But exactly. If it were not for this theorem, if we did not have this theorem, S4 could have a bisymplectic structure, because our B classes, let's say, or B cohomology, B-dram cohomology is larger. It also includes in the degree 2 the one forms in the singular hypersurface.
So accidentally we may have this non-vanishing thing. Exactly. That's a good point. And then there is the next exercise, no, which is
yes. So
which is a bit more sophisticated, but it's this idea.
Yeah. Recalling from the picture from below, we have the singular hypersurface, this Z, in which we have perhaps this this element that defines a volume form inside, well, a symplectic structure inside of the foliation. So it must define a volume form when you apply the highest degree possible exponential to it. But now we could think that the whole Z, being a foliation, is what we usually call a cosymplectic manifold. So cosymplectic means precisely what the image that we have in mind. So we have a foliation by symplectic leaves, and we have a particular direction that is transverse to all of them, that is connecting all of them in a way. So this is precisely what we have in here. Yes, what we have in here is the class A. This represents the symplectic form in each of the leaves, and this B is, let's say, the symplectic, let's say a pairing between the normal and the transverse direction, if I recall correctly.
Yeah.
So let's go through the proof, but it's the proof is the formalization of this idea. So we have a bisymplectic structure with non-empty singular set Z. Of course, we are asking for at the very least, let's say we have we are asking for the Z to be a vibration over the circle. So this is a well well-posed problem, let's say, in this case.
Yeah.
But yeah, given that we have fibers, in this case, we are denoting them by F. They are the symplectic submanifolds that lie inside of Z. So each of them have dimension 2 times n-1 or 2n-2, if you will. So second, yes. Now this all of these symplectic forms can be connected by a globally defined closed form, but you can think of its form. So this gives us A. This A is the representative of this global to form that restricts to symplectic form at each of the leaves.
Mhm.
It's important to note that this is not a symplectic form globally. The Marcutus-Orno theorem only gives us the power up to n-1. So
Yes.
in particular, to the power of n, this could vanish. It's possible that it will vanish. If
Yeah.
we think back of the expression that we had before, I don't know if I can, well, if we think in local coordinates, these are the x's and the y's. Before I had an equation with z and t and all the x's and the y's, this A has the x's and the y's.
Perfect.
Okay. And now
That's very good.
Mhm.
Go on. Sorry.
And now, if we take if we take any of these leaves, take a particular leaf, of course, this is a class in the homology. Let's say in the singular homology of the manifold. So it can be paired with its Poincare dual that lies in cohomology. We can think of it as the ramp cohomology, perhaps. So we denote that by B. And this B, I believe that should represent the other directions, but I'm not so sure about that. So maybe Eva, you will want to add something on that.
Well, yeah,
So
I mean,
basically-
no. I mean, this B, well, by the way, I was thinking that this B is not, it's good for Cavalcanti because he talks about log symplectic, but for the notation is not optimal, but it's okay. I was thinking about that. No, that was I was thinking as that B, we should call this C. No, I don't want to add anything else. That's good. I mean, you are using here Poincare duality that maybe not everyone has been working with this. But I mean, well, this is an advanced, you don't have to understand, let's say, the complete proof, but the idea of the proof is exactly what Joachim said, lies on Z. And that's a little bit the big power of proof of all the theorems that we have been using in b-symplectic. That's why I thought it was very important.
Mhm.
So do you want to add something, Joachim?
No, I think that's all right. Of course, here we have some consequences of that.
Yeah, and then we have all this thing about CPN, that this exercise, I mean, well, ideally, it would have been done to have done it before the exercise that Pau did, right? Because the first question is, what are the obstructions, topological obstructions for a manifold to admit a b-symplectic structure? And then what about if I have already this manifold, are there obstructions to be toric, b-toric? This is exactly the kind of questions that we were answering with the exercise of Pau. So this is indeed very related. I mean, this was before, we didn't have time to comment before, but I think it's good that people look at these resolutions and may ask questions by email, maybe.
Mhm.
Okay,
Yes,
there are 30 minutes left. So I like, Joachim, thank you very much. This was very useful. Indeed, as always, in my planning, I'm now going to share my slides. My slides, I have some of them are already in, as you will see, in a different color, because I knew that I wouldn't have time to, I wouldn't have time to go over all my slides because, well, I mean, usually this is what happens. So I'm going to do this in full screen. By the way, if you look at the decoration in my house, you see that I have next to the guys that are watching me, that still don't have name. I hope that you send me by chat names for these two guys with the popcorns, my audience. today I have here some DAX. Okay, and this is because one of the examples that are very important applications in b-symplectic geometry are in fluid dynamics. And this is one of the examples that I have in the slides at the end of the slides, and they are in violet. And I put them in violet because I know that this would go to next Tuesday. So next Tuesday, I'll talk about the DAX, and the DAX are going to be important also for my general talk. But today I wanted to show you something else that I have here on my shelves. That's a present. I have to say that that's a present that I did to myself, okay? Do you do presents to yourself? I hope you also do presents to yourself. It's important. So that's that's this. If you look at it, it's a model of the solar system. So one of the applications we started to discuss already in the problem list is the restricted free body problem, which is about the satellite, okay? And in the Earth-Moon system that we want this satellite to be back. We want the satellite to be back home. And if you think about this, the fact that the satellite comes back home, the satellite can do many things, but coming back home mathematically means to have a periodic orbit. Today, I'm going to talk about periodic orbits here. So that's, I have this, and I'm going to do this with the power of contact of B forms, okay? B forms are going to be fundamental to find a new class, a new family of periodic orbits for the restricted free body problem. And well, here at the beginning of my slides, indeed you find, I don't want to go into this because this is what Joaquin has been commenting, but I left here in the slides a little bit. Well, these are other results. Obstruction theory, thinking like homology can give you some abstractions. These are the results that we commented, and asking, and somebody asked the other day about this, the singularization, okay? And what is the difference between b-symplectic and symplectic? And I said, well, a good way to look about the difference is to think about boxes, okay? You want to organize your room, you put things in boxes. So I want to put in different boxes of different colors these objects, which are symplectic manifolds or m-symplectic manifolds. That was the question that was asked. And for this question, the answer is, well, we could look, for instance, at the obstruction theory and understand that there are different obstructions. Indeed, this is something that it's not done, it's not written down, but if you have, you consider an exponent of singularities that are of higher order, you can repeat the proof that Joaquin was saying, and you get new obstructions. And it's interesting. This is not written in the literature, but they are more or less the same. And so you have, these obstructions are more or less well understood. And to give, and maybe the theorem that puts everything into its box is a kind of the singularization. And this was addressed, this is a question, this is replying to a question that was addressed by the audience on the last class. What is the difference between b-symplectic and symplectic? This is to understand what is the relation between these boxes. And the relation, what we have understood somehow so far is that we have this Darboux theorem and the action angle theorem. We have the Delsan theorems also for symplectic and b-symplectic. So the question is very natural, the question we got the other day. Okay, if we have all this kind of polytope theory, are we doing the same? Is this a deja vu? Is this a dream we are having each another day and we can never wake up? Are we doing the same once and another and we are publishing it, but it's the same? And the answer, and this is also connecting to this observation, very wise observation that Joaquin did in S4, we don't have any symplectic structure, we know. Joaquin has shown now that it doesn't have any b-symplectic structure. And in the case of CP2, it's not b-symplectic. This comes with the obstruction. This is the last exercise that we were showing. But it's folded symplectic. And the reason is that any compact four-dimensional manifold is folded symplectic. So is there a way to put some order in the boxes? And this is a theorem that I showed some sessions ago, but I want to go back to it because this, what it does for you is to put things in boxes. It tells you, look, if I have a BM symplectic manifold, I can desingularize it. So it means I can provide this manifold with another structure that you understand better. That's the desingularization process. And the other structure that you understand better is either symplectic, that symplectic geometry is much more well understood than b-symplectic geometry, or folded symplectic. And this depends on the fact that your exponent might be even or odd. If it's even, so if it's 2K, then you can desingularize by symplectic. And the reason is something that Joaquim and Pau explained in the problem sessions, is that when you have these torus, and also observed by Pablo, this wonderful torus that Pablo was drawing the other day with colors. When you go through the critical set, you have a change of orientation of the area form. That's why a b-symplectic form cannot be desingularized as a symplectic structure, but it can be desingularized as a folded structure. And this change of sign is what gives you, in this case, this obstruction to having this desingularization. In particular, let me add to the obstruction theory that we already discussed the following fact. If I have a B2K symplectic manifold, it admits a symplectic structure. So in particular, all the obstructions in symplectic geometry apply to this guy, B2K. You may think in these terms, or you may think in the terms that this helps you understand obstructions in symplectic geometry. But well, there is a discussion that we could go on forever. Do you fix the critical set or you don't fix it? I mean, if I don't fix the critical set, the question is more difficult. And if I have a symplectic manifold with odd exponent, then it admits a folded structure. But the converse is not true, as the sphere, four-dimensional sphere, tells us. The four-dimensional sphere is always a good example in geometry, okay? So, well, and how do you do this desingularization? Well, this is a proof. Essentially, the general principle in life is if you don't like something, change it. And let me add, change it as soon as possible, okay? So, well, what don't we like? This is indeed, as Joaquim was writing, in coordinates, this is a form in the most general form, not Darboux. We are writing in the most general form. This is a B2K, I'm doing the B2K case. And let's say, identifying what you don't like, it's important. Maybe you don't like singularities. Maybe this is not your course if you don't like singularities. But if you don't like singularities, you want to kill this guy. A priori, you want to integrate this as the differential of a function. And you can only do this if the exponent is even. That's the reason. This is an integration problem. It's a thing of finding signs that match. And indeed, well, this is it if you want, this is a proof. Therefore, it's a bit technical. Okay, you don't have to understand, but you have to understand that what we do in this proof is to just essentially change what we don't like with the differential of a function. And this function, indeed, we don't have only one function, but we have a family of functions by defining them in a neighborhood of Z. And then by doing this change, we get this symplectic form. And that's how the proof goes, okay, by taking out the singularity. And let me go back now. I want to, of course, understand the restricted three-body problem. But the restricted three-body problem, the formulation, I mean, what we did in the problem is going to be what Joaquim did in the resolution of the problem is going to be basic. I'm going to use problem 1 in list 1, which was solved by Joaquim. And I'm going to do this, I'm going to restrict that computation to an hypersurface. So then what do I have? What I will have is no longer symplectic. It's going to be contact. As I said the first day, contact geometry is governed instead of by a 2 form, by a 1 form that satisfies this condition. And of course, this is a course about singular symplectic geometry. So I will talk about singular contact structures. But a little bit, I mean, a little bit of general culture about contact geometry. This is good. The first one is, what is a contact structure? You can think of you can think of this geometry given by the form, but what plays the role is the kernel of this form. And this is what you call the contact structure. And then to have one form or another, one is multiple of another. So what is this condition that we have here, that alpha wedge d alpha n, that alpha wedge d alpha n is a volume form. If you apply this condition in dimension 3, which I think today it's enough for me to think in dimension 3, this n is going to be equal to 1. And then in dimension 3, this is the standard contact structure. You have alpha, this form, this would be the Darboux coordinates in contact geometry, okay? You can always write alpha in local coordinates this way. And therefore, it's a computation that could be in the list that the kernel is given by these vector fields. You just compute the vector fields that paired with this one form give you Z. This is the kernel, okay? Then let's compute the differential of alpha. And here is where I apply this condition that I was mentioning, that the wedge is askew symmetric, anti-symmetric. So we need to change the sign. And then what I get when we do alpha wedge the alpha, this is an exercise, please do it. You get the standard volume form. So the condition of alpha being contact means exactly it's equivalent to the condition of alpha wedge the alpha be a volume form. So it's also related to volume forms, but now on odd dimensional manifolds. And why odd dimensional manifolds? Because we're going to restrict to a hypersurface, a Hamiltonian system. And why do we want to restrict to an hypersurface? Because if we take as Hamiltonian the energy of your system, we want to consider what we want to understand what happens at a certain level of energy. And this makes a lot of sense physically. And for the restricted three-body problem, this is fundamental. It depends on the energy level that you consider. So I'm going to talk about energy levels in the restricted three-body problem, but because I'm a geometer and we have been talking about abstraction theory, I could now ask the same kind of questions we were asking in symplectic geometry. Do you have abstractions for an odd manifold to admit a contact structure? But before that, do you have examples? Well, this is the mem of the Hopf vibration. By the way, Pau, this is what I wanted to show you. There is a video in YouTube of Niles Johnson, very nice video where you have the Hopf vibration. So the Hopf vibration, and this is an exercise that I left here unfinished, but it's a computation. It's a very easy computation once you have the right coordinates, as always. Once you have the right coordinates, or once you have the right approach to the problem, you can solve it. And here, if you work with these coordinates here, okay, these ones here, which are the coordinates, complex coordinates in C2, then this one form, which is a complex form, it's a contact form. And then the red vector field, you compute it and you get this. But you can compute it further. You can do the change of coordinates of u and u bar. And then remember that when you do the partials, if this is the conjugate of u. So if you go from complex coordinates to real coordinates, you're going to get a surprise of what this vector field is. This vector field is linear in these coordinates. That's what I leave as an exercise. So essentially, this is the mem that was popular on the internet some months ago. Now I arrived some months late, maybe 1 year late, no, some months late, okay? Which is, it's all about whatever, the Hopf vibration, and then the other guy always has been. Indeed, it's all about the Hopf vibration, because if I show you this vector field and you are a geometer, you say, well, this vector field is a red vector field. But I show this picture to my friend, Daniel Peralta, he will find something else. And now what's going on? Okay. He will tell me, no, Eva, this is not the Hopf vibration. He's going to tell me, this is an Euler flow, a Beltrami vector field. Is this the same? And this is, okay, I said deja vu, but this is not deja vu. This is what we will see, because today we will have no time to see this. These are in the, but I have put on a spoiler the slides that are in violet, I explain this, but this is what I will explain next Tuesday. How a contact, how there is a mirror between fluid dynamics and contact geometry. And you can go through the mirror. This is what I will explain. So this is an exciting part of the course. But talking about general culture, we don't really need this, but there are essentially, I wanted to say that there are two sorts of very important contact structures. The overtwisted, that you can visualize them by saying that you have a twist, that you have a disk in dimension 2, where you can write this disk in this way, and your kernel of alpha contains this, such a situation. The tangent to the kernel of alpha contains this kind of sphere. You can also think in other terms, and I think this is going to be more clear. If you are in dimension 3, this would be an example of overtwisted structure, which would correspond to this picture, in which if you look at the kernel, it goes several times around itself. So it overtwists, and that's where the word overtwist comes from. And while here, if you look at the planes, maybe they go once to pi, but around the circle, but they don't go and twist like crazy. So the second structure doesn't twist. So you say that it's tight, okay? Because it doesn't twist. So this is a word that you could use. I mean, this doesn't move, this is tight. Okay, this is tight because it doesn't twist, and this one twists. And this language comes from the fact from this class of examples were found by Eliasberg in dimension 3. And then at that moment, people knew, for instance, that any 3 manifold admits a contact structure. This is big news, okay? This is saying, what are the constraints for, we know that in symplectic geometry in dimension 4, not every symplectic manifold admits not every manifold admits a symplectic structure, but in dimension 3, all the manifolds do. That's a big surprise. But at that moment, Eliasberg, who is one of the main characters of the theory, tried to understand how they were related. And indeed, what was very easy to prove, and this was done with something called like the H principle, which is I will not talk about, is to construct overtwisted. So overtwisted, essentially, it's easy to construct from topological constructions. And tight is complicated. That's a little bit the message. And why I say this, because I will identify a tight structure associated to the restricted three-body problem. So that's quite good. And in higher dimension, this is Eliasberg, this is Borman, and this is M.E. Murphy. In higher dimension, the proof was very hard. And it's not true that any manifold admits a contact structure. You need a condition which is called almost contact, which I will not enter into this, but I can say it's a topological condition. It's a condition of the type that Joachim was saying, that you can even encode, not as easy as with a cohomology, it's a little bit more complicated, but it's a topological condition. So this is a little bit my 2 minutes of general culture on contact geometry. And now let's go back in business. Let's go to the restricted three-body problem. Okay, I go back to the computations that Joachim did, which I recall you here. What was important is that Joachim obtained this formula. And this formula, it's a B3 symplectic form. Okay. And well, this is where we have been working on. Now, contact geometry comes when I take a level set of energy, which means I take the Hamiltonian of my system, which is the total energy of the system. In this problem, remember the Hamiltonian was the total energy of the system. And I restrict to an hypersurface. Then I look at the restriction, and then I look, well, this restriction cannot be symplectic because you restrict to something which is a dimension. The question is it contact? And the answer is it's contact whenever you have a vector field, which is on your symplectic manifold, which is transverse to this level set, and it preserves the symplectic structure. This is what it's called Liouville. Well, that satisfies the condition of Liouville vector field, which is that Lx omega equals omega. That's what you need, okay? When you have this condition, then you have a contact structure. The problem is that now I want to do this computation in the place in which Joachim left it. I want to consider a level set of my Hamiltonian, okay? And I want to check that it's if I take a level set of the Hamiltonian with this particular energy, I want to check that what I get is a contact structure. I have a little problem with this Hamiltonian. And the little problem is where my hand is. My hand is over the T. It's a problem because it depends on T, this Hamiltonian. It means the Hamiltonian or the energy of the system depends on time. And that's a bit problematic because we want a contact structure that doesn't depend on time, okay? So in order to address this, and this could be, and this is a bit hard, I mean, this could be an exercise. This has to be checked. I'm going to now tell you the result without doing the exercise, but this is a computation that would be needed. You need to change to what is called rotating coordinates. Once you change to rotating coordinates, the Hamiltonian also changes. And the good news is that in rotating coordinates, the Hamiltonian is T independent. If you like physics, okay, you can interpret in this guy that you add here, the Coriolis force. If you're a mathematician, you say, oh, I just made a change of coordinates. I am very lucky, I killed time. But if you're a physicist, you are in business. You know what you are doing. You are adding the Coriolis force here. And here, a nice picture that I didn't do, it's from NASA, okay, where we have something that is called the Lagrange points. Lagrange points are important, are very important still in astrodynamics. I mean, if we want a satellite to move and we want to use the less consumption of the satellite, it's known that it has to go around these Lagrange points. And the reason is that they are extremal points of the Hamiltonian. And this is what they are, the Lagrange points. They are critical points of this function. And then a natural question is, what are the periodic orbits? Why do I ask this question? Because I am here. I send a satellite, well, inside this little ball. This is nice. I like it. It's a self-present. I mean, but I really like it. And well, it's very heavy. So if somebody doesn't behave, I can even throw it. But the main point of the thing is that you have a satellite and you want the satellite to be back. So this is why you want periodic orbits. And here periodic orbits, which is something like as a mathematician, you've heard 1,000 times, makes sense in the sense that you send a satellite. And if the satellite doesn't come back, then what we have is this thing in the news. There is a satellite that is going to fall down. And everyone says, don't worry, most probably will fall down on the sea. But how do you know this? Well, I mean, there is a lot of mathematics behind this question. This is a whole world. Indeed, there are people studying debris, just people specialized in what is called debris, which is the satellites that never come back. But okay, if now I'm going to talk about periodic orbits, I'm going to do this from the theoretical point of view. But of course, there is a lot of perturbation theory going on because you send a satellite and conditions change. That's why this is a whole important thing. And there are people like Ed Bruno who work in Princeton and work in NASA. This proves that theoretical mathematics goes hand in hand with astrodynamics. Okay, so what I'm going to show for you is by using this picture of the Lagrange points, I'm going to show you that the level sets of the Hamiltonian admit a contact structure. Well, I'm going to look at the level sets of the Hamiltonian. These guys are indeed, well, they are indeed three-dimensional manifolds, okay? But here I am representing this in two dimensions. So looking at this picture, I know that for low energy level sets, there are three connected components. And when the level set is bigger, when I say low level sets, it means that the level set is smaller than the first one of the level sets of the first Lagrange point. When it's bigger, then you have two. And this depends on counting these components here. You can even use this picture to count components. And the question is, these are components, these are three-dimensional manifolds, are they contact? Well, I could say this is a computation. This is not true. This is a paper of 80 pages. This is more than a computation. But this is something proved by a number of people, including Patternet, Frauenfelder. I always forget about who proved this. Albers, Frauenfelder, Van Coort, and Patternet proved that this has a contact structure. But there is a problem in this business because these connected components are non-compact. So what they do is to compactify them. And they compactify them, what I'm explaining you is the result of these guys, using something that is called regularization and something called Moser transformation. And this compactifies, so gives you compact three-dimensional manifold. And you can totally understand how are these manifolds. These manifolds are projective spaces from a topological point of view, each connected component. And then indeed, what's nice is that this connected component between the Earth and the Moon, it's a direct sum. I mean, it's a connected sum of two real projective space. Question is this contact? We know that this is contact because it's a three-dimensional manifold, but that's not the question we are asking. We are asking, does the symplectic form induce a contact structure? And now, I mean, I don't have time to do these computations, but I'm lucky because these guys did it for me. They proved that these structures are contact. And they are these kind of tight structures, which makes them so special, because this is an example, let's say, in celestial mechanics, where you have tight structures. So that's interesting. I mean, that's a little bit the general culture. Now, well, I mean, let's be serious, okay? Let's put ourselves, we are in the last 5 minutes of the class, but Eva, tell me, does this admit a big contact structure? I mean, why do we want, by the way, these contact structures, and what is the relation with these periodic orbits? I said this the first day, and I'm going to recall it. There is a famous conjecture. It's not a conjecture that will give you $1 million. It's not in the list of conjectures that if you solve them, you get $1 million. But this conjecture is solved in a number of cases, in particular in dimension 3. And in three-contact compact manifold, the red vector field admits at least a periodic orbit. Remember that the red vector field, this is something I said, but let me recall that the red vector field is just given by these two equations. With respect to alpha, you take that the contraction of alpha with R equals 1, and the contraction of R with the differential of alpha equals 0. This gives you a unique vector field that is called the red vector field. Okay, so we are interested in the dynamics of this red vector field, and Alan Weissman was the first one to conjecture that, of course, this was true. And he thought, of course, this is true because he was thinking of a class of manifolds for which that was true. And he was thinking of restriction of dynamics from problems restriction of problems in R2N with the standard symplectic structure. I mean, he had some model in mind, and in all those examples he was thinking of, this was true. So he conjectured it in general. And this has become one of the big important conjectures driving symplectic and contact geometry. And in dimension 3, this was proved by Taubes, and his proof is very interesting, okay? And indeed, it takes a while to understand this proof. And I recommend a commented version of the proof by Michael Hutchings. But what's very important is that they prove, these guys, is that if you have a smaller level sets, so level sets below the first Hamiltonian, the first Lagrangian point, sorry, the regularized planar circular restricted three-body problem is going to have a periodic orbit, say closed, but it's the same as periodic orbits with each energy C, okay? So the message is, this is published in one of the very prestigious journals in mathematics, which is Communications in Pure and Applied Maths. So these guys prove the existence. So this means if you can give me periodic orbits, you get a publication in Communication of Pure. Well, this is not true. but you get an important thing. Maybe you don't get your paper published there, but you get an important result. So it's very important to get new examples, like in the three-body problem, to get new solutions of the three-body problem. So the restricted three-body problem is it's a let's say it's a toy model. It's a simplified toy model. It's a very simplified toy model of the three-body problem, but it's a starting point. Okay, so this is an important thing. Can you give me new families of periodic orbits? And I have good news for you. So B contact geometry has been important to get these families. So what is B contact? So essentially is do a graffiti of the former, put B everywhere, and it works. Let's say, remember that we have been working with these B forms, and we have the right to think that a B contact structure is just a B form of degree 1 satisfying these conditions. So I have good news to tell you. Well, I mean, I have included here the proofs that I'm not going to explain, that we could prove that if you have a three-dimensional BM contact manifold and the critical set is compact, there exist infinite many periodic orbits on the critical set. So that's, let's say, a general theorem for any three contact manifold admitting a singularity of this type, where here the singularity of BM contact type, it means that the one form has a singularity of order. So it's of this type. And the proof is very simple. The proof is using symplectic geometry, because the restriction of the red vector field is just Hamiltonian on Z. That's the message. Then let's go back to the restricted three-body problem. Can you tell me something new? Yes, I can tell you something new. We start with this B3 symplectic form, the one that Joachim computed. And what's beautiful is that with the Hamiltonian that I showed you, the Hamiltonian already, once you go to these rotating coordinates, that this is a Liouville vector field. So you get a B contact structure. It would be good to just apply this previous theorem, but life betrays us because the singular set is not compact. It's a cylinder. But still, you can prove that there exists infinite number of periodic orbits. And this is the proof. The proof, let's say, I don't want you to now look at the proof. I want you to see that the proof has 3 steps, okay? And then the main point is that the red vector field is Hamiltonian, is tangent to the critical set and Hamiltonian there. And that's the main point. Even if it's not, if the critical set is a cylinder, then this family of periodic orbits is just the fibers of this cylinder. And that's something we proved. And so this is a new family. This is an application. And this replies another question I got the other day. Do you have application of B Hamiltonian dynamics? Others. This is an application. This is an application of B contact geometry to find a new family of periodic orbits. Why I know this is a new family? Because this critical set is what people in celestial mechanics call the space at infinity. Okay, and this was not known before. So this is a new result, and this is something. This is a theorem. It doesn't have names, but I should have put it. It's a theorem that we proved with a former student of mine, Cedric Holmes, and myself. So this is a beautiful, beautiful application. And well, I mean, this was what I planned. This is the end of my class, and indeed, I have other slides, but this was the plan. I will start here in the next class, because in the next class, I need to see, by the way, why I have these ducks here. A natural question is, Eva, why do you have so many ducks at home? I don't know, but Joachim and Pau knows that I have yellow ducks. They are not here. And yesterday I was looking at something in my house and I found 3 more ducks. And my husband tells me, why do you have all these ducks? I don't know, but these ducks were there before I proved any theorem in fluid dynamics. But what I can tell you is that these ducks are going to be very important next Tuesday. Next Tuesday, what I will do is to prove that we can put a contact structure connected to the movement of the ducks. And this is going to be very powerful. And I will use what I will construct a mirror between this red vector field. So I will then say, okay, do you have periodic orbits? How can you see them? Blah, 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 blah. This is what I will do. And a dream is to understand what are the escape orbits in celestial mechanics. And the way to understand them is to prove the analog of Einstein conjecture, what is called singular Einstein conjecture. And so this will be the start of my next class, okay? And this will be my last class. The one of Tuesday. Then I will have the public lecture, and the people who have attended this course will understand, and there will be the only ones in the audience who will understand the relation between these DAGs and the restricted free-body problem. And I will, in my general public talk, indeed, I will explain what happened indeed to 29,000 DAGs that were lost in the ocean and why they were lost. But of course, it will be a public talk, so no mathematics, it will be blah, blah. Okay, but next Tuesday, it will be mathematics. So next Tuesday, I think this is the first day that I finish the class just 5 minutes after the end of the class. I think Joachim and Pau will thank me because they will be able to have the lunch before dinner. And so I'm going to stop here. Next Tuesday, let's go to this fluid dynamics and this connection to escape orbits. So this will be really applications of the geometry to what I wanted to explain the first day class. So I think that's the end. So if you have questions, I mean, today class had these two parts, a little bit more applied and more abstract. But if you have questions, I mean, you can ask me now. There are still 24 participants. That's very good.
Hi, may I know that in your singular Einstein conjecture, this P positive and negative, how you choose these 2 points, or it's not important for any?
Yeah, I mean, well, indeed, that's a good question. How you, I mean, initially, that's a good question. If you, I mean, initially we had this, I mean, these are the singular, this, I could have more points, right? These are points that have to be at the critical set. That's the answer. And this replies this question. But if I just look in a neighborhood of this point and I don't look at the rest, so what I see is this thing here. So it's a escape orbit. So what I will show next day is I will show a way to understand existence of escape orbits in a neighborhood of this point. I will prove the singular Einstein conjecture in the case in which the manifold has a lot of symmetries. That's a little bit the conclusion. And I will use the work of Karen Uhlenbeck, which is quite impressive how you relate one to the other.
All right.
Sure. Yeah. So your answer is that these two guys are on the critical set. I mean, yeah, now you could, why don't you take 3 on 4? Yeah. I mean, I could generalize this definition, but first I want to just say that I have something that is topologically a circle, and I mark some points, and these points have to be at the critical set. And these points correspond to zeros of the red vector field, which I can have because alpha can have is such, you have alpha such that the red vector field can have zeros. Chung. Yeah, so this indeed, Chung, I mean, you remember that we had been looking at this picture many times.
Yes.
When we were in Paris. But we didn't know how to interpret this. And now we know, let's say, now we know how to interpret this. This is good.
Yes.
Do we know how to solve the Einstein conjecture in general? No. We have some ideas, but I think that this is a very ambitious project.
Okay.
Again.
Yeah, that seems amazing. I mean, this result is amazing. And I'm happy for you and City. Yeah, great.
Yeah, there's still a lot of work. And with Joachim Chung, I want to inform you that because you were at the beginning of this dream in Paris, and with Joachim, we are constructing the fluid homology. Are you proud of us?
I'm so proud of you. Yes.
So Joachim, yeah, by the way, I mean, I will show you this. We are still, I mean, we are working on this. It's a very, I like it a lot. It's a very cute theorem. We have a theorem. I mean, we have constraints. I mean, we even have a version of Hofer, of a theorem of Hofer, one of the theorems of the papers that you showed me in Paris, but we need to put some conditions on some symmetries on the manifold, essentially because you want to control the orbits that go to the critical set and the orbits that don't go to the critical set. And essentially with Joachim, we are splitting this, just saying it very, 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 very briefly. So yeah, this has to do with our dream in Paris too. So
yeah,
next
I will be
step.
looking forward to know more.
Yeah, but there are many things to do. For instance, I mean, we still need to look at this connection to vortex dynamics.
Definitely, yes, yes.
And we need to do this before Boris, right?
Okay. Right, we will try. Yeah.
Okay. Okay, guys. Well, I mean, the class of today had 2 different paces, and the second pace was a bit quick. But I really wanted, let's say, to get to the point in which you understand that we have applications to celestial mechanics, and the details are in the papers. And I just wanted a little bit to relate also this to general culture of obstruction theory. I hope I convinced you about this. And we have a raised hand here. Go on. We have somebody who raised a hand. I'm going to stop sharing because then I see that.
Hello, Professor.
Yeah.
I want to ask about what is the H principle?
Yeah, the H principle is a hard. It's like you know, I was going to say something very rude. I was going to say like it's the ugly sister that you don't want to show your friends. Or the ugly boyfriend that you don't want to show your friends. No, the H principle, it's a theory that, let me say it with words, I mean, it's a whole theory, it's a big world, okay? But in a way, to put it in a box, I would say that this has to do with the formation, okay? We have learned in this class how to form symplectic structure and b-symplectic structures with the path method. But the path method is not powerful enough. Sometimes we need harder techniques. And essentially the H principle already was used long time ago. I mean, that the first application of the H principle are 2 embeddings of manifolds. And essentially the idea is that you want to solve a problem. You know how to solve a linear version of this problem. And then you can deform the solutions of the linear solution to your actual solutions. This is a little bit, but it's a whole theory. And it's a theory that probably started with immersions in Riemannian geometry, already inspired by Nash, I would say. But then Eliasberg and Gromov did a whole theory. So I said H principle, and I said it, if you look at me, I said it, H principle. I didn't want anyone to hear. Because I mean, it's what is used, but it's not the purpose of this course, of course, to explain what is the H principle. I mean, the H principle is very hard, and there are experts that use this. I would say that I am a user of the H principle, but I know what other people have done it, and I try to apply it when I have only applied it once in my life. Yeah, thank you for the question.
Thank you very much.
Okay, I think that was the hand that was raised. Yeah. So we don't have more questions. Today we're going to finish in time, and more or less in time. So thank you very much for your attention.
Hello, Professor.
Yeah.
Can you hear me?
Yeah, we can hear you. Yeah.
The CP2, which you mentioned earlier. I have seen it in my course, but I don't know much about it. And so, could you please explain the CP2?
Repeat what you say. The second what?
The CP2. I don't know much about
the example
it.
of CP2. Yeah, example. Yeah, exactly.
Yeah.
You want it? Yeah. Let me go to that slide. Okay. Let me share. 1 second. Yeah, the example of CP2. So she's asking, share screen. Okay, well, I mean, it's enough. I don't need to, if I do this, I see your faces, so I think it's better. So, well, you are asking about the fact that there is an exercise in the list in which we prove this. That CP2 is symplectic, this is something we know. We know not only that CP2 is symplectic, we know that it's toric manifold. So this means that it's symplectic, and we know that it has an action of a torus. This is a 4-dimensional manifold, and it was Pau who showed that it's toric, because the image, I mean, this was the example that corresponds to the triangle. Okay, so this is why we know it's symplectic. It's a 4-dimensional manifold, and she's asking, how do we know that it's symplectic and that it's folded symplectic? That it's folded symplectic we know because it's a 4-dimensional manifold. So all of them are folded symplectic, because this was proved by Ana Canas da Silva. I didn't prove this result, I stated. And how do we know that it's not bisymplectic? And this is the exercise in the list that maybe Joaquim, you can share it because you have it in front of you. This is the exercise that we commented. I mean, it was in the last, you have it in front of you.
Hello. Thank you. Thank you, Professor.
Yeah, let us show you, because we have this is an exercise in the list that it's solved. So essentially we apply, and Joaquim had it in front, so he's gonna project. I mean, it's there, but let me show you. Yeah, it was the last page.
Yeah, here, right?
Exactly.
One of the CPNs.
So we have more than CP2, CPN. So we are learning more. So Joaquim, do you want to explain this in 2 minutes?
Well, 2 minutes.
Well, I mean,
yeah,
take your time.
No, it's actually a very precise explanation. So by this theorem that we have in here, by Cavalcanti, in exercise 1.7, we saw a refinement of the Marcoux-Osorno theorem. So we don't only have this form such that its power n-1 is non-degenerate. We also have this B form that lies in the two cohomology that satisfies that this product does not vanish, but its square must vanish. So you need to have nilpotent elements in your cohomology. You need to have elements in your degree 2 cohomology such that their square is 0. However, you don't have these elements in CPN in general for n greater than 1. Yeah, so in H2 of CPN, you will never have elements such that their square is 0. That's the main obstacle, and the explanation is that you have one generator for this group, and that generator you cannot square to 0 because
I have just remembered, Joaquim, that when you were my master student in the master course, that we had a list of exercises in the RAM cohomology, and I remember that precisely you computed the RAM cohomology of CPN. I just remembered, indeed.
Yeah.
So everything connects back in life. Exactly. But we didn't have the same list of problems because then the RAM cohomology we didn't spend time. So finally, you see something you did in the master is useful now. Yeah. Finally. So that's the proof. That's the proof. Exactly. That's very good. That's perfect. So you not only this replies your question. The person who asked. Not only that. I mean, not only we have proof that CP2 does not admit a bisymplectic structure, but all n. So this is fantastic for n bigger than 1 because of this reason. I'm very happy how this class went. I mean, it has been very rich. I hope that people that are following, I mean, we are close to the end and we still have around 25 people connected. This is very good. I'm very proud. And okay, next Tuesday, we are going to finish this adventure in bisymplectic geometry by finding this. I mean, today I tried to convince you that we could find new solutions of the restricted three-body problem. I think this is very cool. But I will convince you more by showing how you can apply this to finding first escape orbits in celestial mechanics, and that these escape orbits, yeah.
Hello, Professor. I have a non-theoretical question.
Okay.
Sometimes we need to read mathematical works by foreign scholars. I'm confused whether it's better to choose the original English version, which is difficult to read, or the translated Chinese version.
What a question translated to Chinese?
Sometimes we need to read mathematical works by foreign scholars. I'm confused.
Okay. You need to read this, okay, in the class. Okay. And?
So the English version is better.
The English version is better than what?
Oh, okay, thanks.
No, I'm sorry, I didn't understand.
I think basically her question is about whether she can find something on this written in Chinese.
Yeah. I think that, look, I discovered, thank you, Chung. I discovered that I can use, the other day I was trying, I mean, you can use the chat. Thank you very much. You can use the chat. Let's do this. You can use the chat and put Chinese and I will Google Translate. I did this the other day. Okay. This means that more or less I will understand. So that's a good idea. That if you want to ask me,
I think, sorry, I think her question means whether she can find papers like m-symplectic geometry or like Floer homology in Chinese.
Okay. Yeah, I don't know. Yeah, thank you. I thought that you were saying that and now I understand that it's easier to read Chinese. I don't know. I mean, Chung, do you know this? Do you have translations to Chinese of works of? Do you have maybe some journal that translates papers to Chinese?
So far, I don't know any of them. No.
You don't know. So I don't know, but yeah, that would be a good idea indeed.
Yeah.
Unfortunately, I mean, I don't know any Chinese, as you know. But well, at least I can tell you that you can ask me in Chinese in the chat and I can Google Translate. I mean, but yeah, papers in Chinese, I don't know. Maybe when Joachim learns Chinese, we can write a paper in Chinese. I have high expectations on my PhD students, more than on myself.
That's very high.
Okay, thank you very much for your participation. And now, yes, now Joachim, Pau, let's go to have lunch. And the rest, you can go and have dinner or see you soon. Okay.
Excuse me.
Yes. Yeah, Jiayang, let me know.
My network is so bad today. But I have a stupid question. When we talk about the celestial problems, why we want to consider the...
Yeah, you have network. I mean, Jiayang, we are not listening to, I mean, we are not hearing you because of this network problem. So my suggestion, Jiayang is asking something about the example in celestial mechanics, but we cannot hear her. My suggestion is that Jiayang, you send me an email.
Yes.
Because we cannot hear you today. Your connection is not good enough. Send me an email and I promise that I will reply your question at the beginning of Tuesday and in the beginning of the class. Okay?
You.
Okay. Okay, guys. Thank you. Thank you, Chung. Thanks everyone for attending. See you next Tuesday.
Everyone. See you on Tuesday.
Bye.
See you. Bye.
Bye.